All right. Okay. Let's take a look at MathBreeze before we start. I want to look at the announcements. Okay. So nothing. Oh yeah, just one new announcement. All right. First, starting with these. Okay, that's next week, Wednesday, October 7th. We have 2 chapters due, 2 sections. All right, and that's the multiple choice. And then Monday, on this coming Monday, October 5th, we're not going to meet on Blackboard Collaborate Ultra. We're just going to I'll post something right here in the announcements and tell you what to do. It'll probably be telling you to watch some videos that are in some of these sections and do a problem set. Okay. Now this is one new announcement in section 00. That's this section here. I posted some textbook exercises with solutions from chapters 015 through 037. Okay, so for quite a few of them from the textbook. All right, so I just you have a PDF there that you can refer to. Okay, for extra problems. All right. Now, I'm going back to 024, 023. Somebody pointed out to me that I didn't cover, I forgot to cover the last question on the third problem set in 024, 023. So I want to cover that, something called the intermediate value theorem. All right. So somebody pointed that out to me in an email, and I realized I have to go back and cover that, and then we'll continue on from where we left off. So first of all, a function's continuous on an interval. We spoke about continuity at a point, like continuity at C, but it's continuous in an interval. That's an interval on the x-axis. All right, so it's continuous here if it's continuous for every point in here. Like polynomials, for example, have no discontinuities. Polynomials are continuous everywhere, so it's good to remember that fact. All right, so we want to talk about something called the intermediate value theorem. Let me write that down. I'm going to write down what it is precisely, but imprecisely, we could say a continuous function doesn't skip. It doesn't skip values. All right, so that's just an imprecise way of thinking about the intermediate value theorem, that a continuous function doesn't skip over a value. So the example I'd like to start with is a continuous process, which is how children grow in height. All right, so let's say a child grows in height from 50 inches to 60 inches. At some point, they're going to be 55 inches or 53 inches in height. They're not going to skip over a height. They go through everything in between. So if they go from 50 inches to 60 inches, they go through every height in between, including 57.8296, whatever. They go through every single height in between because growing is a continuous process. All right, do you agree? Okay, you don't all of a sudden jump an inch and then jump another inch. You have to go through everything in between. So that's what I mean by a continuous function doesn't skip values. All right. So let's say we use that example, and like I said, I'll write out the intermediate value theorem. Well, let me write it out now. Let me write out the theorem. All right. So let's say if f of x is continuous on, let's say, AB, every point between A and B. Okay. Okay. And let's say we have K is in between. It doesn't have to be necessarily. Let me just write it out in words. K is that value that won't be skipped over. If K is between the beginning value and the end value, okay, this is like those heights, 50 inches and 60 inches, and K is somewhere in between, then f of x must be equal to K. But let me write C. Let me write f of C equal K for some C in AB. So that's how we write it out. Now, like I said, it's nice to just remember this little phrase that a continuous function does not skip values. So let's see what how this means that. How this means that a continuous function doesn't skip. So let's say this function starts at f of a at the beginning of this interval. It ends up at f of b at the end of this interval. K is somewhere in between these two numbers. That means that the function has to be, can't skip K. The function has to be equal to K. All right, that's all. Do you understand the intermediate value theorem? All right, it can't skip over K. K is in between this and this. It can't skip over K. All right, so here's a picture that goes along with this. All right, so let's say the function starts, here's, let's say, A, and let's say this is B. Let's say the function starts here at this level, this y level, f of a. It doesn't necessarily go up. It could go up, and down, but I'm going to draw a function that goes up. And let's say it ends up here, up at f of b. Okay. That means it has to go in between. Like, let's say we pick K. Let's say K is here. If I'm going to draw something from here, let me draw this. I didn't draw this further enough up. This is up at f of b. So it starts off at this level, f of a. It ends up at this level, f of b. All right, and if I'm drawing the function going from here to here, this is K, level K. Can I connect this with this and skip over K? If I do that, the function's not continuous, you see? I can't skip over level K. It has to cross level K. So here's, at this point it crosses K. This would be my C. Okay. Do you understand the intermediate value theorem, just the phrasing of it? Okay, good. Okay, good. All right, so that's the phrasing of it. And just think a function doesn't skip values. That's the intermediate value theorem. So sometimes we have little examples, little exercises having to do with the intermediate value theorem. I'm going to do the one that has to do with growth that I just mentioned. So let's say this is my function. It's going to be a line, really, and the form mx plus b. I'm using it because it corresponds to that growth function that I mentioned. All right, so let's say a child, this is, let's say, a growth function. Okay, x is years. And f of x is inches. All right. So let's say at 8 years, how tall is this child? So let's see. All right, let's just divide here, 2 into 8. So we have 20 plus 30, 50 inches. All right, and let's say what happens at age 12. Okay, so this is 8 years, all right, at age 12. So this one is age 8. This one's age 12. Okay, we have 5 over 2 times 12 plus 30. So let's see where the ending height, this is 6. 5 times 6, we have 30 plus 30, we have 60 inches. So in these 4 years, the child goes from 50 inches to 60 inches. All right. Okay, so by the intermediate value theorem, f of x goes through all in between heights, all values between 50 and 60. Okay. For x going from age 8 to age 12. Okay. All right. So that's what that means. So let's do a more typical example. Okay, so let's say f of x, and let me pick let's pick this one. Okay. And let's say the interval is, let's say 0, 5. Show that f of x is equal to let's show that f of x is equal to 7. Okay, in other words, for some c value in there, that it does hit 7. All right, so how do we show that? We don't have to find what c is. Sometimes we could do that. You know, we could definitely do that. I'll show you that as well. But we just want to show that it does hit 7. So by the intermediate value theorem, well, let's first of all, we have to, in order to use the intermediate value theorem, we have to say that f of x is continuous. So usually we use polynomials. So let's say f of x is a polynomial. That means it's continuous. The reason why we mention this is that means so can use intermediate value theorem. So we have to mention that it's continuous. Otherwise, we can't use the intermediate value theorem. Okay. So now we say so by intermediate value theorem, and we'll just write it like that. Okay, and we'll set it up like this. The beginning point is f of 0. We'll write it in a column, so one underneath the other. F of 0, plug in 0, we get 4. Plug in 5. Sorry, f of 5. Okay, so we have 25 plus 4 times 5. 25 plus 20, that's 45, plus 4 is 49. So we're going from 4 to 49. Now, 7 is in between. That means we can't skip over 7. Okay, so therefore, we can't skip over 7. This is writing that out mathematically. We can't skip over 7. We write f of c is equal to 7 for c in 0, 5. That's it. That's all we have to say for this problem. By the intermediate value theorem, we know that we do hit 7 because 7 is between the starting value and the end value. Now, what is c? Sometimes it's easy to find, sometimes not. And you're not necessarily asked to find c. Okay, what is c equal to? Well, let's try to find it. All right. So we want to know, you know, the f of c is equal to 7. Okay. Or maybe, okay, so what do we have? F of c, just when is this equal to 7? When do we get 7? So we just solve this, x squared plus 4x plus 4. Solve for x and we'll get c. When is that equal to 7? That's what we're asking. When does it hit 7? Subtract 7 from both sides. We just did minus 7, minus 7. All right, not in luck. This doesn't look like it, this doesn't factor. All right, so then we would use the quadratic formula. Okay, so we have x equal, that's what I mean, sometimes it's easy, sometimes not, depending on if we get something that factors, or sometimes we can't figure this out at all. We just know, we use the intermediate value theorem to show that c exists, but not to find c necessarily. In this case, we could find c because we have the quadratic formula. So I'll do it quickly. Negative b plus or minus square root b squared, 16, minus 4ac over 2a. So we have 16 plus 12. 16 plus 12 over 2. That's just, sorry, 12. Okay, so here we have 28. I'm going to simplify this. You can just go straight to your calculator and figure out what this is, or I'm going to just simplify it a little bit. This is 4 times 7, so here we have 2, 7 over 2, and let's write minus 2, plus or minus square root of 7. Now, which are they both? Could they both work, or does only one work? Well, it has to be, our answer has to be in 0, 5. Okay. So it can't be minus 2 minus root 7. It must be minus 2 plus root 7 for in 0, 5. Let's make sure. Let's use your calculator now. Let's figure out square root 7 and add 2. Sorry, square root 7 and then add minus 2. Okay, just makes it in. Okay, this is approximately equal to 0.645. Okay, so it's in my interval. That's good. If I ended up with two things that weren't in the interval, then I'd have to check my work. Something went wrong. All right. All right, let's do one that's a little, well, let me do another one that's also typical. This is like the one in your homework. All right, so let's say we have for f of x equal to, let's say we have 2x squared minus x. So that f of x has a 0. In other words, f of x is equal to 0 in interval. This is also another typical kind of problem. F of x is equal to 0 in integral, let's do, let me do it. Just 1 second. Okay, let's do 1/4. I don't want to use fractions, so let me pick something else. Okay, let me do interval. Okay. Just a minute. I don't want to choose, I want something that's like very simple here. Okay, so I'm going to use another polynomial. I want to keep it simple. I want to keep the numbers simple. Okay, so let's do this one. All right, so let's make it 2 and 4. Just that. Show that f of x has a 0 in this interval. And we're going to use the intermediate value theorem. Now we could just factor this. This factors x minus 3, x minus 5. So 3 fits in here. So if we just factor it, we say the answer is yes right away. But with the intermediate value theorem, let's see how we would proceed with the intermediate value theorem. So you start by saying f of x poly, so it's continuous. All right, so by intermediate value theorem, f of 2, that's equal to 4 minus 16 plus 15, that's 3. F of 4 equal to 16 minus 8 times 4 minus 32 plus 15. That's 31 minus 32, that's minus 1. Okay. Now I want to make sure it doesn't skip over the value 0. 0 is between. That means that f of c equals 0 into 4. So that's it, done. That's all you have to do. Now if you want to know what it's equal to, this time we can do it without the quadratic formula. So that's why I want to pick an easier one. Without the quadratic formula, what is it equal to? So we want to know, when is this equal to 0? X squared minus 8x plus 15. What x value makes it 0? That's what we're asking. And is that x value going to be between 2 and 4? So we have x equal 3, x equal 5. This is the one between 2 and 4, not this one. So that's the one we're talking about. So that's our C value. So sometimes we can easily solve for the C value. All right, before we also fairly easily solve for the C value, we just need the quadratic formula. All right, sometimes we can't find the C value. It involves maybe figuring out the zero of a third degree equation, and we can't always do that. Second degree, we have quadratic formula, but if it's third degree, we might be able to figure it out, we might not. But that's it. All right, so the problem on the homework has to do with the last type of example that we did. All right. Okay. I'll give you just one to do like this, one more. Okay, let me make one up. That's a little bit different. Okay, let me see. Let me make this one up. All right, so it's 0 in the round parentheses. It's equal to 0 because we know at f of 2 it's not in between. To mean in between, I use the round ones. In between 2 and 4, that's why I use the round. Okay. All right, so let me look at this one. All right, so let's say here's another one. For f of x equal, this time I'm using third degree. Show that f of x has a 0 in interval let's do 0, 3. Okay. All right. So what we do is look at the starting value. This is what I call the starting value. The starting value, plug in 0 here, and we get -1. Let's look at what I call the end value. Plug in 3, and we get 2 times 27. Okay, so that's, just write it in, 2 times 27 minus 3 minus 1. 54 minus 4, we get 50. Okay, minus 150, 0 is in between. Okay, so that means we are going to, the function can't skip over 0. It's going to be equal to 0. All right, no skipping. Remember, that's what it means, no skipping values. Okay, so you'd have to write f of x a poly I don't understand. Sorry, I don't understand what you wrote there in the chat. I don't know either. Oh, are you figuring it out on the calculator? You figured out on the calculator where it's equal to 0? Is that it? Okay, I'm not sure what you meant. All right, so we're going to write f of x a poly. Oh, okay. Okay. Okay, no problem. Okay, f of x a poly, so that means continuous. Okay, so we have to say that because otherwise you can't use the intermediate value theorem. By intermediate value theorem. Okay, now we're going to figure out start point, end point. Yeah, I mean, we did that already. We did start point, end point. So by intermediate value theorem, 0 is between f of 0, f of 3. So no skipping 0, f of c equals 0. in that interval. Okay, so what is C? Let's see if we can figure it out now. When is that thing equal to 0? Let's see whether we have 2x squared minus x minus 1. 2x cubed minus x minus 1 equals 0. Can we figure that out? It's not a quadratic. We don't have a quadratic formula. So sometimes what we do here is guess. Okay, so can you look at this? Just guess it's going to be a small number. Guess a small number, plug in to get 0. What do you think? X equal what? Just pick some small numbers and see if you hit upon it. So sometimes you're, in the book they have a couple of questions. Right, 1 works. 1 works. Okay, try it. X equal 1. So that's just guessing. Okay. 2 minus 2 minus 1 equals 0. All right. And 1 is in 0, 3. Okay. All right. Okay, I don't understand what you wrote there, Christian. Did you get some other zeros of this? Okay, we know that 1 is one of them. If we want to know where else it's equal to 0, there are other methods for doing that. That's where you can actually divide by x minus 1, and you could figure out 2 more zeros as well. All right. But so this one we just got by guessing. Usually you can't guess. Usually you just know, oh, it's equal to the value, but you can't figure out that it doesn't skip that value. In other words, f of c is equal to that value, but usually you can't figure out what c is unless you're solving a quadratic, all right, or a linear. Of course, you could always solve. All right, so that's the intermediate value theorem. I just wanted to not skip over that. Okay. All right, so I want to go on to, we were in O3b, so I'm going to continue with that. And we were looking at derivatives. This is our definition of the derivative. That's how we get f prime of x. If we want f prime only at a specific value, then sometimes we use the other slope formula. Sometimes we call this one, usually we call definition of the derivative. And this one is usually referred to as the alternate definition. Alternate definition of the derivative. So if we wanted the general function f prime of x, we'd use this one. If we wanted, let's say, only the value at a number like 2, for example, f prime of 2, we could use this one. We could also plug in a 2 here. All right, so those are the 2 definitions of the derivatives that you'll come across. All right, let's do one little example and maybe finding a derivative, and then I want to talk about functions that are not differentiable at a given point. All right, so let's just practice finding one derivative. Let's say we have this one. We'll do a polynomial. All right, so we'll use the definition of the derivative, not the alternate. Okay, limit h goes to 0. And now we're plugging in x plus h here. So let's look at this again. First, we're calculating f of x plus h. Plug in x plus h here and here. So it's just, instead of x, write x plus h. Okay, and here too, instead of this x, we're writing x plus h. Now we're doing minus f of x. I'm making sure that I use parentheses so that I get my signs right. Because when we open up, it's going to be minus x squared plus 2x. So we just have to expand and do this calculation. Yeah. Oh, you're right. You're right. You're right. It's not squared. Thank you. Okay, thanks for correcting that. Okay. Yeah, I got to get rid of that square. Okay, so here we have x squared minus 2x. That's what we have, squared minus 2, not squared. Okay. Okay, good. And let me put the limit in front here. All right. Square this out, x squared. Since we square this out so much, so you should just remember what that is. Now, multiply through by minus 2. So we have minus 2x, minus 2h. And now, open parentheses, minus x squared plus 2x. Now, everything without h should cancel. So I see this minus 2x cancels with this plus 2x. We have it plus x squared canceling with a minus x squared. Everything else has h in it. So let's divide by h now. So we'll divide by h here, and we have 2x. Here we have h plus h. And here we have minus 2. And now limit h goes to 0, this disappears. This goes to 0. So we end up with 2x minus 2. All right, so we showed that f of x, for this f of x, the derivative is 2x minus 2. So that's what we showed. So this, let's make this part A, finding f prime of x, because very often there are two parts to these problems. And let's say we find, instead of, I won't do the whole tangent line here, I'll just do find slope at x equals 5. Okay, so that would just be f prime of 5. Maybe we'll also do the tangent line, okay? Let's might as well. Find tangent line. Find the equation of the tangent line. At x equals 5. All right, so if we just use this form, then we really have no work to do. Just fill it in. Okay, so we have the slope we already got, it's 8. That's our slope. X minus x1, x minus 5. Here we just have to figure out y1. This we have to figure out. All right, in other words, plug in 5 into our function. Okay, that would be just plug in 5 into the original function to get the y value. All right, so that's 25 minus 10, 15. Okay, so we're done. That's the tangent line. The tangent line at the point 5, 15. All right, so that's one typical type of question for this section. We have to find f prime of x. Usually you have to know how to find f prime of x really for 3 types of functions. Polynomials, like we just did. Something like square root of x or square root x plus 5, that's another type, right? And one other type would be something like 1 over x or 1 over x squared. All right, so those are just, 3 different ones that we typically do the calculation for. All right. Okay. All right. So now let's talk about, I just wanted to end with functions. Example of functions that are not differentiable at a point. Or let's say more simply, do not have a derivative at a point. At one specific point. At x equals some value. So we want to just look at examples like that. All right, so first we'll just look at some pictures. Of functions that don't have a value at a specific point. All right, if they're not continuous, then definitely no derivative. Okay, there's no tangent line here. It's not even continuous here. All right, so that's one example. Even if it's a removable. Okay. Okay, so that's no f prime of c. I'll write it like this. F prime of c does not exist. For this one too. Okay, but here's the one that's we're more interested in examples where the function is continuous but no derivative. So this is an example where you have a point. Okay. All right, so we have some sort of point. There's no tangent line at that sharp point. Sometimes we have another example we'll come across as a function that looks like that. Also a different type of sharp point. A different type of point. This one's called a cusp. It's a different type of point. So let's look at some examples. A specific example, absolute value of x. We want to show that f prime of 0 does not exist. Okay, that's what we want to show. Okay. By actually going through the definition, pretty simple to go through the definition, but let's do it. Here's f of x. We said it's equal to absolute value of x. Another way of writing this is it's equal to x if x is greater than or equal to 0. Just drop the absolute value signs. If x is less than 0, stick a minus in front, and that'll make it positive. So that's how we open up absolute values. All right, so we're going to do it like this, using the 2 lines, the piecewise defined function. Okay. If we graph absolute value of x, it's the line y equal x here, y equal x when x greater than 0, and y equal minus x. So this is the line y equal x here, and this is the line y equal minus x. This is the line y equal x. Okay. All right. So we'll see. I'll show this. We'll see soon that the derivative of a line, what do you think the derivative of, just on the side, okay? Let's look at this function. I just want you to guess. What do you think that the derivative of that is? Just guess. Remember, derivatives give us slopes, right? So someone just guess what the derivative of that is. What would make sense, just because derivatives give us slopes? What would make sense for the derivative of that without going through the calculation? What's the slope? The one is the y-intercept. You know, this is y equal mx plus b. So the slope is 5, right? So the slope is 5, so it would make sense f prime of x is equal to 5. We'll see it using a calculation, but f prime of x is just 5. That's it. It's the slope, because after all, derivatives give us slopes, and lines have the same slope throughout. They're just, you know, the tangent line, if you take up a line, the tangent line to a line is exactly the line again. You get right back to the line. Okay, so it would make sense that if you have a line with slope 5, the derivative is the slope 5. Okay, because derivatives give a slope. So the derivative of this piece is 1. The derivative of this piece is minus 1, and they don't connect. All right, so if we want to find the derivative, let's say we want to find the derivative at 0, we're going to use the alternate definition. All right, so we're going to have to break it up because the function is two different things to the right and the left of 0. So in order to take this limit, we're going to have to break it up. All right, we're going to have to break up into limit x goes to 0 from the right and limit x goes to 0 from the left. Because f of x is two different things to the right and left of 0. So do I use minus x in here or x? Well, it depends on if I'm coming from the right or the left. So if I'm coming from the right, I'm using x, the function x. Okay, let me just write that clearer. I don't want you to think there's a minus sign in front. This is x. So we have f of 0 is 0. So we have x over x, which is 1. Limit x goes to 0. Okay, x over x is 1. We can reduce that. Now, if we're coming from the left we're using, to the left of 0, we use the top line. We use minus x in our expression. Remember, we're allowed to reduce when we take these limits. Reduce it when we get minus 1. These are not equal. So that means the limit as x goes to 0 of f of x minus f of 0 over x minus 0. That's f prime of 0. That's what f prime of 0 was. Does not exist. So that's how we show that f prime of 0 does not exist. Actually try to calculate it. Use the alternate definition. And you see you get 1 from the right, minus 1 from the left. They're not equal, so f prime of 0 does not exist. Okay, so that's how you actually show it. Instinctively, you see, well, the slope here is 1. The slope here is -1. So it's, all over here it's 1. All over here the slope is -1. And 1 and -1, they don't connect. Okay. So that's an example of a function that's continuous at 0, but f prime of 0 does not exist. Okay. We'll do one more. Well, I think we're going to show in general f of x continuous. Well, let me say c. Let's use a specific value. F of c continuous. That means f prime of c may or may not exist. Usually it does for the functions we come across, but it might not. If the function comes to some sort of sharp point, then it won't exist. But we will show that f prime of c exists. If the derivative exists, then f of c or f of x is continuous at c. So derivative, one way derivative implies continuity. But the other way doesn't work. This way doesn't work. So I'm going to just box the one that does work. Derivative implies continuous. Okay, this is the long way of writing it. The short way, the way you should remember it, is derivative implies continuous. But not the other way. The other way is not true. Continuous doesn't imply derivative. Okay, so this we're going to show. We'll show this, that derivative implies continuous. All right. Okay, I think I'm going to end here. Next time we'll do one more example of something continuous. I'll just show you which example we'll do next time. We'll just finish this next time. Here, this function, x to the 2/3. Okay, I'll graph it. This is what it looks like. It comes to what I call the cusp, C-U-S-P. That's the graph. All right, and we'll show that f prime of 0 does not exist. All right, that's one example. Another one we'll show too. One last one. Actually, we won't show this until, actually we could show it, yeah. We don't need the next section. I was thinking we need the next section to show it, but we don't. We can show this also. So we'll show this next time. Let me graph this. Here you see it comes to a point. So this is similar to absolute value of x. All right, but let me just show you, this one's different. Let me show you what this function looks like. It looks like this, and then it swings around like this. So it doesn't come to a point, but the tangent line, you see that tangent line? It's vertical. Vertical, that means slope infinity. So here, f prime of 0 is infinity. So that's why this one doesn't exist. So these are two different types, really. All right. Here, this one is more similar to the previous one we did. Here, f prime of 0 is infinity, so it doesn't exist. But we'll show these. We'll continue with this next time. Okay, any questions? All right. Okay, so Monday, remember, we don't meet on Blackboard Collaborate Ultra, but I'll give you something to do in MathBreeze. You'll check the announcements and you'll see what you should do. Okay, have a good weekend, and I'll see you Tuesday. We'll meet again Tuesday. Okay, thanks.